Okay. Welcome back, everybody. Today, we are going to go a little further with our lint bot. We are working on a bot that can run in CI, continuous integration or continuous delivery scenario. And this bot is going to check our Kotlin code, make sure that it is nice and clean according to the KT-lint tool and standard. And we're going to be doing that with a number of different tools, exploring them pretty in depth. Gradle is going to be our build tool. Kotlin's going to be our language. Vertex is going to be our web server of choice. And then KT-lint obviously is going to be our lint checker tool. In the stream a couple days ago, we set up a multi-module Gradle project. We battled some annoying directory issues for a while, but we got through that. We then organized our Gradle build files to kind of better support multi-module projects. So if you'll remember from the last stream, we set up a number of things in our root build.gradle file, primarily our libraries and our dependency versions, so that we could organize and keep track of these across our modules and make sure they're all the same. And then we added a number of things that apply to all of the different submodules. And we're going to get rid of this Java compile section because this is a pure Kotlin project. This was a desperate attempt last stream when we were trying to figure out our build issues, and this isn't needed, so we're going to remove that. What else? And then finally, we in the last stream we set up and talked briefly about Vertex, the Vertex Web Toolkit, and we talked about some options, and we briefly covered the event loop, and we set up a request handler so that when we run this project, right, we can see that there is a basic request handler that is running on port 8080, and it will return something. So this was just to get Vertex up and running, show you how easy it is to get up and running quickly with Vertex. So today I want to go through and talk about the Vertex event loop more in depth and in detail, because if you're coming from utilizing Spring or servlets or any of the other blocking web frameworks out there in Java land, this might be a little foreign to you. And in particular, if you haven't ever worked with or done any socket programming, and particularly non-blocking I/O or NIO socket programming, it's going to be a little difficult to understand maybe why we're doing some things here, particularly in our request handlers, and why we're trying to be so careful about kind of not blocking this thing called the event loop, right? And if you've heard of the event loop, you've probably heard of this in JavaScript and such, but this, you may not have seen this in Java, so I want to cover this and go through this thoroughly, because this is going to be pretty important for a bot, a web server that we want to stay responsive, and that's going to be doing a lot of, blocking I/O type work, right? So just to show what we looked at the other day in the other stream, what we did was we created a simple single request handler, and then in order to demonstrate that we were in an event loop and we can't block the event loop, or we don't want to block the event loop, we just did a thread.sleep here, and we set some options when we spun up our Vertex instance, and we said, let us know if we block the event loop for more than 500 milliseconds, and when you do that, show an exception, right? So that we know and we can figure out where that exception is and where we might be blocking the event loop. So in the last stream, we threw in a thread.sleep here, just to kind of demonstrate this, and we'll do this again right now. And so what will happen is if we go ahead and request this again, Vertex is going to complain and say, hey, we blocked the event loop, right? And fortunately for us, it will also then tell us exactly where we did that, right? So it'll tell us, hey, the thread is blocked. You blocked, this thread for this amount of time, and here is where you did it, right? So pretty straightforward, but this is why we're going to talk about the event loop more in detail, because this fundamentally works very differently from many other Java web frameworks, right? So it's probably easiest to start off not in code and just look at this at a bit of a higher level. And actually what we'll do is we'll just do a text file in here so that we can show this. So let's take a look and let's talk about what this is. So in a blocking web framework, the behavior is quite a bit different. So in the blocking web, in a blocking framework, and I want to be clear, Spring has non-blocking support, has had non-blocking support for a long time. A lot of web servers and web frameworks these days can actually run on top of different kind of socket engines, right? Netty, Grizzly, and a bunch of others. So I'm really just talking about if you're, this is kind of just in a more general case, right? So if you're running at a traditional kind of servlet or Spring or older application, what happens is that anytime a request comes in to your web server, what happens is that the servlet container that you're running in, or the framework or whatever that might be, is likely spinning up a new thread, and this is where all of your work is done, right? So whenever a new request comes in, it just spins up a new thread, and then basically it calls into your code, right? And so this is a really nice, simple, clean model for the most part, because you can write your code in a synchronous fashion and you can do really whatever you want in here. You do need to be a little careful when you're going into different threads and things like that, but by and large, for the most part, this makes it really easy to do things. But at the same time, this also does have some drawbacks. So if you get a ton of requests at once, or if you have limited resources, ultimately there is a limit to how many threads can be spun up. And there is also a limit to how many threads should be spun up given your resources, right? So when this happens, and you ask for a thread and you switch around and you ask the CPU to do different chunks of work on different threads, there's going to be resource contention, right? And so this inherently kind of hits a model depending on how much horsepower you have on your machine. And so if you have a really big server with a lot of horsepower, this is great because it will scale and work quite well. But if you want predictable or more predictable performance, and if you want to utilize less resources to, say, do the same amount of work, that's where, and depending on the workload that you're doing, a non-blocking I/O based server or NIO might be for you. So what does NIO mean? So non-blocking I/O really starts way down at the kernel level, right? And the idea is that messages or things are coming in over the network card, and the operating system allows you to listen to that and basically keep calling it in basically what is effectively just a while loop, and saying, hey, give me messages, give me things that are happening on this socket, right? And you can actually tie into that, and I have on my GitHub, There is actually, yeah, an example of this. So I did another stream a while back on building a very basic non-blocking I/O web server in Kotlin. And if we just take a look at this, right, I mean, it runs in one thread. And really what it is it's just a while loop, right? And basically all it's saying is whenever I get something inbound, look and see if I can accept it. And then basically once you get that thing, it basically gets put on another while loop. And basically we just go in this loop and we say, hey, wake us up and tell us when things are readable, meaning there are messages for us to process. And we just process those, right? And so that allows us to handle multiple clients' requests with a much lower thread count, right? And a thread count that we can control. So what does this look like in Vertex? So Vertex runs on top of Netty. And Netty is a very high performance framework based on non-blocking I/O, and it kind of goes a whole number of steps further than say the built-in non-blocking I/O APIs in Java for performance and all sorts of different reasons. But Vertex runs on top of this, and if we kind of visualize what this is really doing, right, is rather than every time a request comes in and spinning up a new thread, what we're really doing is something more like this. We're really basically running a while loop, and basically whenever we get a request, right, rather than spinning up a new thread, we are basically putting that thing essentially on a queue. And basically then the next thing we'll do in the loop is we will basically go through the queue, and we will do work, right? We'll do some work. And we literally just do this over and over and over again. And the work in which we do this, right, is done. We typically have, or what you'll typically have is a thread pool, right? And we might have, say, 4 threads. And basically what we'll do is we'll call, basically it'll use this thread pool and it will do the work with one of those threads, all right? Now, what happens when you get more than 4 inbound requests, right? This seems actually really dumb. Why would you limit yourself to 4 threads? Well, when things are happening or in your do work, there's a lot of places and times where you've done a little bit of work. You've maybe call out to a database or you're calling out to another web service. When that happens, you're just waiting. And when that happens, if you are writing things in an asynchronous pattern like you would, like JavaScript, for example, forces you to do, that will allow you to say, hey, I'm waiting here. Why don't you let someone else do some work, right? And so basically that's what Vertex and that's what Netty is asking you to do. It's saying, hey, we can get a ton of work done with only a few threads if you're just willing to tell us or write your code in such a way that you can at least let us know when you're waiting on something else or someone else, right? If you're kind of willing to share the time, right? And so in that case, right, if we can do that, we can handle an incredible amount of traffic and requests with a lot less threads, with a lot less resource contention. And from that, we'll get more predictable performance. We will better understand, potentially how long certain things are taking, right? And so this is just it's another way of handling and doing, writing web servers and handling requests, right? So again, rather than spin up a new context or a new unit of work for every request that comes in. You basically say, no, I have a finite amount of resources and I'm going to share those resources between all of these people as long as these people, or as long as these requests, or as long as this code is willing to share it with other people. All right. So that's the event loop at a very high level. I'm happy to answer any other questions. If people have any, feel free to reach out to me if you kind of still don't get this concept. Again, this NIO stream as well has a number of videos that I did. So if you still don't understand, building your own NIO server is actually a great way to understand how this actually works. So go ahead and do that. So then that, now that we understand a little bit of how the event loop works, right? Then we have to answer the question of, well, a lot of work is blocking, a lot of APIs are synchronous, a lot of work takes time. What do we do? And so Vertex has actually a lot of different ways to handle this. You can architect your Vertex applications in a number of different ways to deal with this. I'm going to walk you through the kind of the very basic, quick and easy one. And then what I'm going to do is we're going to actually add coroutines support, which the way that coroutines work is actually in some ways kind of very similar to how the event loop works. But we're going to add coroutine support so that it kind of feels a little more native to how Kotlin handles concurrency and blocking work and things like that. So how would we do if we had to do some expensive work, right? How would we do that, right? Where should we put this, or what could we do to make it so that Vertex doesn't complain and this still works? And the quick and easy and dirty way to do this in Vertex is with blocking handlers, okay? And a blocking handler is, again, just as it says in the documentation, it's just like a normal handler, but it's called by Vertex using a thread from a worker pool, not using the event loop, okay? So that's really important. So basically, it does the work on a different thread that is not the event loop, and then basically it allows us to send control back to the event loop to respond or to do other work, right? So let's take a look at this. So if we do, and we're going to have to make further changes to this to make this work a little better. We're actually going to introduce a router here. So let's go ahead and do that. So a router is basically in Vertex a way to do path-based matching and things like that, right? It's exactly what it sounds like, a router, right? So we're going to go ahead and create a router. And change our code a little bit. We're going to pass it Vertex. And then we are going to change this to router dot path route, yeah, that's right, route, and this will be a handler, and then we're going to ask we're going to want our request handler to be our router, and then we're going to listen, right? So we didn't change much here. We just changed who was handling the inbound request, right? So in the case before, we were just saying, hey, throw a request handler on the HTTP server. Now we're going a little further, which will allow us to do a lot more things, and we're adding a router into the mix, and we're asking the router to handle our requests. And we're basically, again, we're just changing this to say anything that comes in on any path here, call this handler. And then when we start up our server, rather than just saying start up, we're telling it what's handling our request, which is the router. So let's go ahead and run this, and we will just verify that what we had before is working the same exact way. So if we go ahead and do this, we're going to get the same behavior, right? We are blocking that thread, which is not good. That's not what we want. That's not what Vertex wants. So what we can do is look at moving this work, this blocking work or this expensive work, into a blocking handler. And we can do this by basically just specifying this, okay? And we're going to log out here, doing some expensive work. And then we're going to responding to request. So with this in place now, oops. We're going to go ahead and run this, and let's take a look at what happens with this. So if we go ahead and run this, it's saying we're doing some expensive work, and then nothing happens. And that is because we need to capture this route. Why is my keyboard shortcut for reformatting code Control-Alt-L? Yeah, that's what I'm doing. There we go. So nothing happened, and that was because we didn't add it on the same route. Sorry, no, it's because we didn't call next, which is what we should be doing. Always call next. So we can set up multiple handlers, and they'll get run in order. And you need to indicate to Vertex when you're done, in these things. You either need to respond or you need to call next, right? So we're going to go ahead and rerun this. And if we do this, we'll see doing some expensive work and then responding to requests, right? Note that we didn't get the warning from Vertex about blocking the thread because this work was being done in a different thread. And one way to kind of check on this, right, is doing the following: thread.currentThread.id. Well, actually, let's just do the name. So if we print out the thread where these two things are being run, we're going to get two different things, right? And so we're going to see that this is no longer on an event loop thread, it's on a different thread. So you'll see Vertex is doing this work on a worker thread, not on the event loop thread, right? So this is kind of the simplest, easiest way to move work that is expensive off to a different thread and do that work and not have Vertex complain about this, right? So this is, again, the simple, easy, quick way to do this. So now that we've got this, now that we maybe understand a little bit more about how this works, let's go ahead and add coroutine support and see how this this might change a little bit. Oh, I need to pull down the latest. On this computer. All right. There we go. All right. So so I'm going to mark this off. So we looked at. We just took a little bit of a brief look at the Vertex event loop. And so now we're going to look at adding coroutine support. And this is, for this we have to do a couple things. So we're going to go to our build.gradle file. And we're going to add both the Kotlin, the coroutines package from Kotlin, and then we're also going to add some more dependencies to our Vertex block specifically for coroutines. So let's take a look at that. So we need the Kotlin Coroutines core, most likely. Yes, Kotlin Coroutines core. Let's go with 1.2.2. Just, well, we can live on the edge here. So we're going to bring in org JetBrains Kotlin-X, Kotlin-X-coroutines-core, and this is going to be version 1.3.0-M2. So, okay, so let's we will pull that in. So we'll pull that into our webhook. So we want coroutines in our project. And then we can also pull in, we also want to add the Vertex coroutine support, right? So this will give us some of the extensions that we need in the Vertex framework to use coroutines, right? So we're going to do Vertex coroutines here. Let's look for this. Yeah, Vertex lang coroutines. So we're going to want to pull this one in. It's going to use the same version as all of our other stuff. This is just going to be Vertex lang Kotlin-coroutines. Okay. So now we don't actually have to add that one because, again, the way that we organize our libraries, anywhere you say, hey, I need Vertex, that will get pulled in. And because we put it in this block, that gets pulled in, which is nice. So now this is where we're going to have to do a little bit of work. So what we want is we want to be able, rather than setting up this blocking handler, we want to be able to do something like this. We want to be able to do something like this, where we do basically this, right? You know, how do we want to best demonstrate this? Let's do this. So let's do this in here, and that way this is kind of out of sight, out of mind. So basically we're saying, hey, we want to do some expensive work. And so we can go to the Kotlin Coroutines overview and just take a bit of a look at how this works. And so I'm not going to go fully into coroutines. I'm kind of going to skip over a lot of things in here. If I can do a separate thing on coroutines, that's, if we want to do that later, but which I will do that later. But basically, coroutines are a way to it's a type of concurrency that they say they're essentially lightweight threads. You launch them, and basically they're very similar to kind of how non-blocking IO works. They're always sharing work. They're always sharing threads. So you can spin up 1,000,000 coroutines, and it won't spin up 1,000,000 threads. It will timeshare and use a number of different threads under the hood, right? So let's do something very kind of just naive and take a look at what happens with this. So there's a number of different ways to launch a coroutine. One of them is run blocking, and it's a way to kind of bridge the two worlds together. So let's do this and see what happens. So if we run this, this is still complaining. And that's because this is not really aware of a coroutines, this handler. And so this, run blocking is a way sometimes to kind of bridge the world of coroutines and non-coroutines, but this is still, just like it says, a blocking piece of work, right? So let's do this. Where do we want to? Okay, so let's look at a different way. So when we added this Vertex line coroutines library, we got a number of interesting additions. One of them is access to the event loop as a coroutine dispatcher. So when you launch coroutines, you always want to do it within a scope. And in this case, we actually want the scope of those coroutines to be tied, all together as a request. And one thing that we can do is we can tie in to the Vertex Dispatcher. So we can, in here, ask for the dispatcher from Vertex. So let's look at this, right? So this is a coroutine dispatcher. It is in the, you'll see this is in the Vertex line coroutines jar. So this is in that extra thing from Vertex that we brought in. And this gives us a coroutine dispatcher, which is how we kind of dispatch work. Or it's kind of the work pool, right? And it uses the Vertex context event loop. So this, again, so it says this is necessary if you want to execute coroutine synchronous operations in your handler. Okay, so now that we have this, let's go ahead and do our expensive work in here. And let's wrap this. And check out what this does. Starting the expensive work. Done with the expensive work. So when we do this, let's see what happens. And again, I'm intentionally kind of walking through a lot of things that may trip people up, to eventually get to where we want to go, right? So if we do this, we have a handler, we start up a new coroutine scope, we ask for the dispatcher, and then we launch this, what do you think would happen? All right, so I'll go ahead and run this. We're going to see. Oh, interesting. So what happened here? We asked the coroutine scope to do this work, and we launched this work using the Vertex Dispatcher, so the event loop dispatcher, and we got the same behavior as we did before, right? So this is effectively, so what we did here, right, we launched a coroutine scope, we did work in a coroutine, and then we responded to the request, okay? And actually, we can actually even make this even more interesting. What if this returned an integer? What if this did this? So let's do this. Dun, dun, dun. Yep, we're gonna have to do this. And then $. So I'm gonna go ahead and run this again. And we're gonna check this out. That's right, because we need to do this. Required unit found int. What am I doing? Oh, you can't use this with launch. That's right. That is right. How would I show you what I'm trying to do? Dun, dun, dun. Dun, dun, dun. I am drawing a blank on how you return something without, let me think about this for a second. Because you can definitely do this. I'm just trying to think of the best way to do it. You can't do it with launch. That ain't gonna work. Dun, dun, dun. That ain't gonna work. Yeah, let's, okay, there we can do this. Okay, so let's do this, and we will take a look again at what happens here. So we do this, we're going to get the same behavior as before. And so nothing really changed, right? We all we did was we launched a coroutine in the Vertex Dispatcher, and this thing ran synchronously as we would have expected, right? Because we're asking we're saying, hey, let's launch a coroutine on the current immediate Vertex Dispatcher, right? So this is going to run asynchronously. Now, there is the async keyword. This is a, and again, I'm not going to go into a ton of this, but this is a deferred coroutine. So what we can now do is this. Oops, that. So now what's going to happen is we are saying required int. Yes. Yeah. Okay, this is where we want to go. Okay, so what this is saying is we're basically capturing this unit of work. We're not launching it immediately, and we want to use it down here. So after we have this, we're going to call this. And we're going to call this random work just to make this a little clearer, right? So and just ignore this for now. I'm just trying to show something here. So the way to get the work that was being done is to use async, because it's basically a deferred thing. And you will have seen this in JavaScript and whatnot, right? This is very similar to how the await thing works. Is you set something up and then you await that result. Okay, but you can only use this when you're inside an actual coroutine. You can only use that when you're inside a coroutine. So what do? Well, there's a couple things you can do. Let's do something a little differently first, though. So let's go back to what we had before, and let's see if we can do this work and get this thing to run, and not block the event loop. Okay. Do I'm posing this now because there may or may not be a way to do this, and so we're gonna kind of butt our heads up against a few things to see what we could do. But let's go ahead and give it a try, right? So what if we used something other than the Vertex event loop to launch our work? What would happen? Think about that in your head, and we'll run this and we will see. So again, we're coming into this handler, we're launching this work into a different thread, kind of very similar to what we were doing with the handler, and then we're responding. So let's see what happens. Okay, so if you were kind of expecting this to return and the work to happen out of order, you were correct, right? So what is happening here? So we are launching some work in a different thread, the dispatchers.io thread, and again, this is just a thread pool. If we go all the way down to the bottom, right, it's just a thread pool. But Vertex isn't aware of this right now, right? That doesn't work. So basically, we've launched this thing, but this handler doesn't know that it should wait for that thing before completing, right? So you'll see, we respond to the request, we're starting the expensive work. But wait a minute, we've already responded to this request, and we didn't wait for the work to be done. So that's not what we want, right? So what do? Well, within our handler, we could run all of our work within the context of the Vertex event loop, and then dispatch that work as we are doing now into an IO launcher. So let's broaden the scope of how we're using coroutines and see what this might look like. So let's do this. So let's do, we're going to bring this up, and we're going to, bring this back to where it was. So we're going to say we're going to do this work in the Vertex Dispatcher, and we're going to bring everything up into the coroutine, right? Now, so this is basically just going to do the same thing, but the work that we're doing is all going to be within here, okay? So again, just to look at this again, same thing as doing, we're starting the expensive work, we're doing it, we're getting the thing, and then we're responding to the request, right? So this is just, again, the same thing that we did before. However, now that we're within a coroutine, we can do this work in another coroutine and have it work properly, okay? So let's take a look at that, right? So before, remember, we looked at something like this, right? We looked at something like dispatchers.io. So that was cool. We dispatched our work in the other thread, right? That was great. That meant we did our work off in a different thread. And then we did something before, right? We did this async thing, and this work. We could then do something like work.await, right? And we can do this now because we're within the context of a coroutine, right? We're within a coroutine scope. And then, just for kicks now, let's just return this, right? So we've made this. So basically, we've done our entire handler within a coroutine scope. We are tying that scope directly to the Vertex Dispatcher, and then we're defining some work that we want to do in an IO block. We're awaiting that work, saying, hey, wait till this is done, and then we're going to respond. So let's go ahead and see what this does. Let's see if it complains about blocking the event loop. And it doesn't complain. As many times as we run this, it does not complain. All right. So this is a lot better, right? So this is, again, us doing work in a handler using coroutines, not blocking the event loops, and we can do this as many times as we want, right? So this now we can. And we can do things, actually, let's do this. So this is a way to do expensive work, database calls, other I/O, things like that. Write synchronous code, not asynchronous callback hell, Mountain of Doom code type stuff, right? You can do all of this in, again, a synchronous fashion and not block the loop and, run a pretty, this is a perfectly, for the most part, for small things, an acceptable solution. There are some things we can clean up. So let's how can we make this a little nicer to look at or work with, right? So, this async and await is kind of silly. We don't need to do that. We just want to do the work and get the thing back, right? So what if we refactored this a little bit and we used this thing called with context. And this is from Coroutines and the work. And we're going to return this. Oops. So what if we just did with context, right? And we'll dive into this a little bit, but so basically with context is essentially a shortcut or a builder for doing kind of what we just did, right? So calls the specified block with a given coroutine context, suspends until it completes, and returns the result, which is exactly what we want, right? We want it to do this work on this dispatcher, run the block on an IO thread, and then return what happened, right? So it's just a shortcut for what we did before, right? So let's just go ahead and confirm that that is the case. And now you see we are getting numbers. We're not blocking the event loop. We're doing the work on a separate thing, and then we're responding back on the event loop, right? So this is pretty cool. Now, one thing to notice is, say we want to do a whole bunch of different things in here, and we if we do this right, this is effectively kind of running in a still in a synchronous fashion, right? So this isn't quite what we want. What we really want, if we were doing, say, multiple things, is and actually one thing to notice here, when we do this, you might expect, and one thing that you're not seeing is when we call this, when we use dispatcher's IO, you're not seeing a new thread for every single piece of work. So if we do this, you're probably going to see one, and then you might see it different. You might see it change 4, 4, 1, right? So this is what I was talking about. Under the hood, coroutines are just using thread pools, but they use something called the way that they work under the hood is kind of with an implementation, I believe, or at least the last time I looked, was kind of what's called a work stealing thread pool. So it will scale the thread pool based on the amount of work and the amount of things that you need to do, but it's also going to reuse threads to try to prevent context switching and prevent spinning up and down threads when it doesn't need to. So for example, when we ran this work and it ran one right after another, it just used the same thread, right? Then I sent another request in at the same time, and it goes, oh, we can use work 1 for this, but hey, this thread might be a little backed up, so let's spin up another thread. And then when the next thing came in, it goes, oh, either one might be busy or one may be killed, so why don't you just reuse 4? And 4 is already done, so you can reuse 4 again, right? So it's basically doing all of this work, and it's sharing a number of threads rather than creating its own thread for every piece of work, right? And there's a bunch different types of dispatchers. There's IO main. I won't get into that. They do have specific purposes for on Android, the dispatchers that you use do really matter, and here they don't matter nearly as much. But this is just kind of an important thing to note. So, but what you'll notice is that we're not doing this work, at the same time, right? So these two things, we could actually do this work at the same time and return, right? So right now, it's taking basically almost 2 full seconds to return this request, right? 0, 1, 2, and it's back, right? But we could do this work in parallel, or it'd be great if we could do this work in parallel, right? So let's do that, right? So let's say, rather than with context, async is another kind of builder or shortcut in coroutines, right? And if we run this, we're going to see not what we want, but we're going to see the request return really fast. And then it's going to return these, right? So again, in order to do this, we need to await this work. So basically what will happen is that we're storing this work, and we're not actually triggering it until we actually want to respond. So this will be kind of interesting. So what will happen is we won't see starting the expensive work until after we've print this, and I'll do here, and we'll say responded to the request. And this work won't actually be triggered until it's actually needed, right? So let's go ahead and see what happens here. So, again, we saw, hey, we printed, and the print lines aren't going to be perfect here, but this will, you can kind of at least see kind of what's going on here, right? So we started responding to the request, and it did this work at the same time. So this is returning in about 1 second rather than 2. So 0, 1, responded, right? And so this allows us to basically wrap a bunch of different synchronous pieces of work or blocking work, and allows for us to do this work at the exact same time. And we don't have to worry about threads. We don't have to worry about that sort of thing. We don't have to worry about a lot of the things that you might have to do with threads in terms of synchronization, right, and joining them and whatever. We can just define these chunks and these blocks of work, and then basically we can await them where we need, and this will all be handled. And again, most importantly, we're not blocking the event loop. We're doing this work somewhere else, and this is all happening, again, right, back on the Vertex event loop, which is great, right? So that's kind of a brief, a brief exploration and look at how coroutines, or how you can use coroutines with Vertex. We basically showed how we can do blocking or long-term work within our handlers using coroutines, and then obviously still respond in the same fashion, right? And the nice thing about this is that our code, for the most part, still looks and feels like it's synchronous code. We're not really dealing with callbacks or nesting or the Futures API, which is quite heavy in a lot of respects. So this is going to be, the ability to do this and write our code this way is going to have a lot of kind of long-term benefits, both from performance perspective, because we can kind of very easily control how and when operations and work is done, whether it's serially or in parallel, and it allows us to really not change much about how we're using Vertex, which is another really great thing. So before we close out, let's take a look. Let's take a little bit deeper look at what the coroutine kind of extensions from the Vertex library, right, from this library. What does this give us, right? So let's explore that a little more, because there might be some other interesting things in there we might want to use in the future. Like I said, right, it gives us a dispatcher, and it's a coroutine dispatcher for the Vertex event loop, right? So this is just like what we were using before. But let's go ahead and look up here. So and we can also then say what else is in here. So if you look at the extensions that are in here, there really isn't much, right? Which is kind of nice. This is one of the things that's great about Vertex is the API is really well designed. So when you go ahead and you add these extensions to work with a different paradigm, or whether it's RX, whether it's coroutines, whether it's any of these other different types of things, the additions to make that work is really simple. So here in this Vertex coroutine class, right, there's a lot of different ways to allow you to write Vertex code and use coroutines, right? So there's things here for awaiting work, right? So basically you can run an asynchronous block and await its execution. So this is kind of a replacement for the handler that's used in a lot of different cases, right? What else is in here? What else might be interesting for us? Await blocking. So here is a really interesting one. So in here, we kind of were manually doing kind of the coroutine work with the dispatchers, right? And if we go back, I'm going to go back to what we had before. We were just doing one unit of work here just to show this. So and I'll pull this up on the side here so we can see it. So await blocking, right, lets us run an asynchronous block on a worker thread. The block is executed and should return an object or throw an exception, right? So looking at this little example here, let's see if we can do that. So let's use await blocking instead, right? And let's see what happens. And again, we're getting the same type of thing. And what you'll notice is that actually, rather than using a different thread pool, Vertex is now using its worker thread, right? So this is the way. This is what's cool about what these extensions are. This is essentially just bridging the gap between the old blocking handler and what we had, what we looked at in the very beginning, where we did, for example, route.blocking handler. This is essentially doing the same thing as this, right? This await blocking function does this same thing. And if we read this, the code's pretty simple, right? We're awaiting the result of this. It's running in a handler, and it's basically just execute blocking, right? This is what we had before. So this is, again, Vertex has things built in it to help kind of bridge this gap. Again, you can use, you can really use these, honestly, whichever way you want, right? It doesn't necessarily matter, but again, it just integrates really nicely with coroutines. You can do a bunch of this work. If you need more fine-grained control, right, you have to kind of do it the other way. But that's just the way it is. But so let's take a look at what else is in here, right? So again, right, like I said, there isn't really much in here, which is great. There is a coroutine vertical, And we may, I don't know if in this example, or if in this project, or in this at some point in this kind of series or stream, we're going to actually even need to spin up a vertical. We probably don't, but we might. That might be something that we do. So what this does is that allows you to spin up a vertical, and it allows you to write your some of your say that your start and your stop functions, right, are in coroutines, right? So and the other nice thing about this is that, by default, all the child coroutines will have the verticals coroutine as the parent scope. And that can become important. The coroutine scope is a kind of complicated topic in terms of, when you start up a bunch of these things, what scope do they run in? If, say, the request was canceled, do all those things cancel nicely, right? This is going to kind of come into play probably a little later on, but again, right, there's just not much here, right, which is pretty nice. So I think that's about it. We've covered a lot. I think we can kind of tick this box off a little bit of, looking at coroutine support in Vertex. We've checked out a lot of different things. We banged our head against different things. We've looked at a bunch of different things, the way to do this. I think I'm going to leave the code the way that this is, and we might improve on this further in the next stream. We might add a vertical, maybe talk a little bit about coroutine scope, although that's a really big topic. So I'm not sure if we want to go down that rabbit hole, but again, right, this is good. Where we netted out is we can now do our expensive or our blocking work in these handlers utilizing coroutines, which should be pretty nice as our project gets a little larger. So if you have any questions, have any things you like answered, anything like that, let me know. I will put this up on YouTube very shortly, so you can watch a replay. It'll also be up on Twitch for a while. And I will check in the code so you can take a look at it, and tag it as well so you can come back to this when you want. And I think that's about it. So thanks, everyone.